So the topic of my lecture today is efficient mitigation of climate change in national and international energy systems. So what we know today is that mitigation of climate change requires a total revolution in the global energy systems. The human-induced climatic warming is mainly caused by emissions of carbon dioxide, methane, nitrous oxide and fluorinated gases. The most important one of these is carbon dioxide. It's emitted mainly from the combustion of fossil fuels, but also from the decline of natural sinks. So that's related to land use changes, for example. The world is still totally dependent on fossil fuels. 81% of global primary energy supply came from fossil fuels in 2013. That's the latest year of global statistics available at the moment. So about 30% came from coal use, similarly from oil use, and about 20% from natural gas, respectively. So what does this total revolution in energy systems means? Here are a couple of graphs from the International Energy Agency, IEA. How would a global energy scenario consistent with the 2 degrees warming target look like when we look at the global energy system from the present to the year 2050? So first on the left side, there are the different sectors where the cost-efficient mitigation measures would be accomplished. So the most important sector there is power generation, about 40% of all reductions. Then transport and industry would both comprise about 1/5 of total. And then buildings would have somewhat smaller role. Then on the right side, there we can see what technologies would be needed and how much in a cost-efficient solution estimated by the IEA. So the most important single technology group would be increased efficiency of all fuel and electricity use. Then renewable energy sources would be equally important, also contributing about 1/3 to the total reductions that would need to be achieved. Then there's also carbon dioxide capture and storage technologies, so-called CCS technologies. IEA is estimating now about 14% share for those technologies. And then there's also nuclear energy with about 7%. A few years ago, IEA was still estimating that CCS would have a much larger role in this, but the recent development with the CCS, both research and development, but also the implementation and demonstration of the technology, they have been quite disappointing in the past year. So now IEA is more careful with that technology. Here's a similar graph from the Intergovernmental Panel on Climate Change, IPCC. And this graph is extending longer until the year 2100. What kind of changes would be needed in all greenhouse gases emissions if we want to limit climate warming efficiently? So first of all, here in the most pessimistic so-called business as usual scenarios, the global greenhouse gases would still continue to increase very strongly throughout this whole century. But what would be needed would be that we would follow this blue trajectory with the greenhouse gas emissions. So that means that before year 2100, the global greenhouse gases emissions should reach 0 or even go negative. So these are just huge challenges that need to happen. So then how to transform the energy systems towards carbon neutrality? I have here altogether 3 graphs showing what kind of toolboxes or tools we have in the box with regard to electricity production. So these graphs are showing the life cycle emissions of CO2 of different electricity production technologies. The emissions are shown as equivalents of grams of CO2 per kilowatt hour of electricity produced. And first, here is the most problematic technology, coal, with different combustion technologies. And you read these graphs so that the yellow part of each bar, that's the direct CO2 emissions from the combustion of the fuel. Then there's also a light blue part in the bar. That's the methane emissions from the process. Those can also be significant. And then there are statistics shown of what we know. So this blue area in each bar, that's the 25th, the area between 25th and 75th percentile of all data that we have. And then the whole extent of the bar shows all of the data that has been collected for this IPCC report. So coal is the most problematic one. Natural gas has about half of those emissions than what coal has. Biomass is not totally CO2 neutral. This is a very relevant and hot discussion topic here in Finland because our energy policy is heavily dependent on increasing the amount of biomass in our energy system. But it's also not totally CO2 neutral. So this red part is infrastructure and supply chain related emissions that take place also with biomass. So then the list of technologies continues. Wind power has very low life cycle CO2 emissions. That's mainly the infrastructure and supply chain emissions. Then there's again coal with another combustion technology, but still very high emissions. Integrated gasification combined cycle technology. And then there is coal together with this carbon dioxide capture and storage technology. So this CCS technology can reduce the emissions from coal combustion very significantly, but not totally. You can see that still there would be some emissions also with that technology. And with gas combustion together with CCS, the emissions would again be a bit lower. Ocean energy, both wave and tidal, have very low emissions. But then when we are looking at all of these lists, we should remember that not all of these technologies are mature and commercially ready technologies. So that's, for example, the case with ocean technologies, that they are still very heavily in the research and development phase, not ready for commercial use yet. Then the list continues. There's geothermal energy, which is also very promising, but it's limited to the areas where we have plenty of geothermal resources. Hydropower has mostly very low life cycle CO2 emissions, but then there are also some very extreme cases, as you can see here, that have been reported. So I would guess that these are mostly due to the decay of biomass due to the construction of dams and flooding of natural vegetation areas. Nuclear power has very low life cycle CO2 emissions, and so have also both of these different solar technologies, concentrated solar power and solar photovoltaic technologies. But mitigation of climate change in the energy systems, it's not only about electricity. That's what is too often forgotten also in the international policies. Our energy needs include also heating, cooling, and transportation. These are all very important, large sectors of energy consumption. So when we are designing efficient measures, we need to have holistic assessments. And for example, in this recent European energy and climate policy, I personally think that the role of electricity has been too dominant, and these other sectors have been more or less forgotten in the policy development. For example, it's very common in Central Europe that heating is taken care of with natural gas. It's also common that the natural gas is coming from Russia and the neighboring countries. So it's not only an important source of CO2 emissions, but it's also an important energy security issue. Then there's a very big important trend taking place in the international electricity markets at the moment. Variable renewable electricity, especially from solar and wind, is increasing very rapidly. And this is changing strongly electricity markets. And conventional power plants are now at the moment facing a totally new kind of business environment. So the demand of their electricity has become more volatile, and also the electricity prices have become more volatile. There are moments when there isn't much solar and wind power available, then the prices are increasing and conventional power plants are still needed, but there are also a lot of times of the year, for example, in many European electricity markets at the moment, that there is a lot of wind or solar available, and that's decreasing strongly the demand of electricity from these other conventional power plants. So the whole energy system now needs to adapt to this change that's taking place. Then when we think about Finland, our northern location is posing special requirements for our energy system. In Finland, the electricity need in summertime is about half of that of wintertime. Then when we look at heating needs, for example, in district heating systems, the winter peak demand can be 6 to 7-fold that of the summer minimum demand. So there's a great variation. In milder climates, the situation is totally different. Cooling needs are higher. Even the annual electricity demand peaks may be caused by the cooling needs of summertime. Then when we think about these holistic assessments of efficient measures to take in energy systems, heat and electricity are fundamentally different. Heat is very easy and cheap to store, but electricity is totally different. The amount of electricity in the network needs to be in balance on a time scale of some seconds. Otherwise, we immediately run into serious problems with the system. So here is a very recent picture of what is happening with the Finnish electricity system. This is hourly data about 1.5 weeks back, when we reached all-time record in electricity consumption here in Finland. That was, I think, a Thursday. So the record is now about 15,100 megawatts. And this is what we had available here in the system. First, we had baseload nuclear power. Hydropower is typically reacting to the daily maximums, just like it's doing there. Then we have condensing power, combined heat and power, both from district heating of the cities and combined heat and power from industry. Then this orange one is wind, and then the blue one is estimated other electricity. And a huge part of our electricity needs was imported during that record day. So it was mostly from Sweden and Russia. In Russia, there were holiday periods of New Year, so that was the reason that there was electricity available for Finland. So we were very lucky that this consumption peak took place exactly that week and not the next week. So I personally think that this is one big current issue in the Finnish electricity system. It's a risky thing to be so dependent on imports in winter time. And what has happened in the past couple of years is that we have been losing a lot of this condensing power from the system. The energy companies have simply shut down their power plants because they are not profitable anymore. Now there's a clear risk that the same is happening also for the combined heat and power in district heating. So this is related to some current research that we are doing. We are participating in a large national scale research program, one of these shock programs. It's called FLEXI, which is studying future energy systems. So we are investigating what is happening in the district heat systems and how they could remain competitive also in this future environment. So this is one case study for Järvenpää, which is ongoing research now in our group. So Järvenpää is a mid-sized Finnish city, and the power plant and the network are owned by Fortum. We are collaborating with them. The network has a modern combined heat and power plant, which is running mostly on biomass fuels. Then they also have heat-only boilers. And then we are making different hypothetical scenarios together with Fortum to see what kind of additional systems or parts of this system would be optimal in different future environments, operating environments. So we are experimenting with large heat storages, large heat pumps, and large solar heat plants. And then we are making simulations with hypothetical future electricity market prices. Here is an example of what kind of simulation we are running for one hypothetical year, so that we have the current actual heat demand, but then we are just testing out with this kind of electricity price profile. So that this is simulating a situation where there would be a lot of wind power in the Nordic electricity system. There would be periods with very low electricity prices. Those would be the periods with a lot of wind power available in this system. Then there would be also the opposite, that the prices would increase very high. So how would this kind of district heat system then cope with this kind of changes? So this is an example of the simulation, what would be happening. I'm sorry if you cannot quite read everything, but I will explain the most important parts. So this brown line here, that's the district heat demand in the city of Järvenpää. It's starting in the beginning of May 2014, and then it's running, this is the winter time when there's the higher demand, and then it's ending in the next May. And this purple one is showing how the combined heat and power plant would be operating in this kind of future electricity market scenario. So the traditional way of this kind of district heat system operation would have been that, of course, this purple combined heat and power plant would have been running throughout the winter. That's the logical thing. Then that's when we need both heat and electricity. But now the electricity market changes are causing a big changes to the operation of the system. You can see that even in the winter time, there are weeks, there are the red times, when it's more profitable to be running just heat-only boilers and heat pumps instead of the CHP power plant. And you can see here is also the periods of electricity consumption by the large heat pump. And here in the bottom figure is shown what is at the same time happening with the large heat storage. So you can see that the heat storage is very actively needed. It's being all the time either uploaded or unloaded, and that's helping a lot to, it's giving a lot of help for this conventional power plant to be operating more smoothly when you have large heat storages that you can use. So these are examples of ongoing research and one very current issue, and that there's a lot of demand also among the energy companies, both here in Finland and everywhere in Europe, to how to adapt to these changes that we are seeing in the electricity markets. So thank you very much for your attention.